Hello, everyone. I'm Stacie Baumann. I'm from Auburn University in the United States. And I'm going to talk to you about completing partial Latin squares with prescribed diagonals. And all of this is joint work with Lars Andersen from Aalborg University in Denmark, Tony Hilton from the University of Reading and Queen Mary University of London in England, and my advisor, Chris Roger from Auburn. And I want to thank the organizers of this conference for putting this all together and making it so accommodating for all of us overseas. All right, so first a couple definitions, and if you were just at the plenary talk, you heard a bunch of these, but a Latin square, L, of order n is an n by n array in which each cell contains one symbol and some symbol set 1 through n. And I'm going to call that set 1 through n Sn. And each of the symbols in Sn occurs once in each row and once in each column. So here is an example of a Latin square of order 5. A partial Latin square is an n by n array in which same symbol set, but now the symbols occur at most once in each row and at most once in each column. So basically it's a Latin square, but some of those cells could be missing. So again, here's an example of a partial Latin square of order 5. And what I'm going to call an incomplete Latin square, a lot of other people call this a Latin array. If you've seen that in the literature, it's the same thing. We just call it an incomplete Latin square of order n. This time, we still have this n by n array, but we can have more symbols than just that symbol set 1 through n. So in this case, I have an incomplete Latin square of order 5 on the symbols S11. So I have the symbols 1 through 11. Again, each symbol occurs at most once in each row and at most once in each column. And just note that not all those symbols have to occur, right? So in this example, I'm on S11, but there's no symbol 7 here, but that's okay. And I'm going to let NLJ be the number of cells that contain symbol J in L. So pick your favorite symbol here. So like I said, NL of 7 equals 0. Symbol 7 doesn't occur at all in L. You could look at where symbol 10 occurs. It occurs twice in L. So NL of 10 is equal to 2. Okay, so I saw a lot of design theorists in the chat, in the Discord, so maybe a lot of you know this theorem, but if you don't, we're going to kind of start from the very beginning. So in 1951, Reiser proved this theorem that an incomplete Latin square L of order n on the symbols in ST can be embedded in a Latin square of order T on the same symbols if and only if we have this condition here. So this NL of J is greater than or equal to 2n minus t. So again, I'm kind of putting this incomplete Latin square up in the corner here. All these other cells are empty and white, and I'm asking myself, when can I complete this? I can complete it if and only if each of the symbols satisfies this condition here. And this, I'm going to call this Reiser's condition throughout this talk, and I'm going to kind of modify it for the different types of problems we're going to see here. And I should say, if anyone has any questions, feel free to just jump in. I'd rather everyone kind of be on board and not get through as much than speed through everything. So feel free to jump in. All right, and I'm going to kind of briefly mention this history. Sometimes I'll go into more depth if I had more time, but this problem that we're going to talk about originally started in the idempotent case. So idempotent, I didn't even define it, but it just means that symbol I occurs in cell II. So we kind of get this property down the diagonal. In this problem, I'm going to put up on the next slide, basically started with this idempotent case, and we had lots of results listed down here at the bottom. But let's skip to the actual problem we're going to talk about today. And that is looking for necessary and sufficient conditions for embedding an incomplete Latin square L of order n in a Latin square of order T. But this time we're going to prescribe how many times each symbol occurs on this diagonal. So, okay, looking at this picture, we're going to take any old incomplete Latin square. I don't care what symbols occur here. And I'm going to kind of prescribe how many times each of these symbols occur on this diagonal outside here. And I'm going to say when is this completable and when it's not. I'm going to try to find these necessary and sufficient conditions, kind of similar to Reiser's theorem. So here's an example. I have an incomplete Latin square of order 4 on the symbols S10. And I'm prescribing symbol 5 to appear once, symbol 6 to appear twice, and symbol 8 to appear 3 times. So this specific example I have here, you can complete. But again, I'm looking for those kind of necessary and sufficient conditions, something kind of similar to Reiser's theorem. And I gave this talk to first year grad students at Auburn, and someone said, does the placement of the symbols matter? So the order that these symbols are on the diagonal. So no. So here's a quick little observation, and I'm going to actually use this observation many times, not just in this context. But if you switch the rows if you switch 2 of the columns in a Latin square or 2 of the rows, you still get a Latin square. So say I had this Latin square and I did want that kind of property where the diagonal was non-decreasing. But in this case, you see my 6 and my 5 are kind of backwards from what I want them. I could just swap these 2 columns, and then I could swap these 2 rows, and I get what I want. So really, it doesn't matter. We don't need to think about the kind of placement. We really just care about what symbol occurs and how many times it occurs on that diagonal. Okay, so kind of the first result dealing with this problem kind of made the problem a little bit easier, right? If we can't solve the problem yet, make it a little easier, see if we can solve that. So what they did was they said, what if we just prescribe almost all of the diagonal? So I kind of highlighted it in red right here. I'm only going to prescribe, I'm going to at least leave at least one cell unprescribed. And in that case, we can always complete it if and only if we have this condition. And this, again, is going to be that kind of Reiser's condition here. But it's a tiny bit different, right? We have this 2n minus t, but we also need to add that f value. So remember that f value is the number of times that symbol is going to occur in that diagonal. So they got this condition. If we have this Reiser type condition, then we can complete this into a Latin square. All right, so what about that fully prescribed diagonal? So for that fully prescribed diagonal, again, that's what this, the sum of the f values means over here. Well, we got that this Reiser's condition and these 2 other small necessary conditions that we're not going to be too concerned about in this talk. If we have that Reiser's condition and these 2 other necessary conditions, then as long as t is greater than or equal to 2n plus 1, then we have that Reiser's condition. So remember, t is the size of the big Latin square, n is that size of that incomplete Latin square. So if it's almost double the size of that incomplete Latin square, or a little more than double the size of that incomplete Latin square, then yes, that Reiser's condition and these 2 other conditions are sufficient. But Anderson, Hilton, and Roger, the same authors, also proved that if this f value is equal to 1 for some symbol, and t is less than 2n, then there exists some incomplete Latin squares in which these conditions are not sufficient. And back in the 80s, when they were working on this problem, they kind of had this conjecture that maybe that's the only condition that's preventing these small examples from not being completable. And it's actually that conjecture we prove. So Anderson, Hilton, and Roger were kind of working on this in the 80s. They've put it aside for a while, and I kind of jumped in, and we were able to work out the details and figure everything out and actually prove this conjecture. Okay, so before I go into kind of a little bit of the proof of that, let me kind of talk about the structure of their proof for those big cases of n. And that'll kind of give us an idea of what we used in these smaller cases. So say I have some incomplete Latin square L here, and I'm going to prescribe symbol 2 to appear twice and symbol 6 to appear once. And I'm going to assume that all my symbols satisfy that Reiser's condition. So here I just did the algebra. We want them all to be greater than 2 plus fj, which you can double check that if you want. Okay, so what I'm going to do is I'm going to make these graphs using this incomplete Latin square. So I'm going to join Ci to sigma j if sigma j is missing from column I. So I'm joining C2 to sigma 2, sigma 3, and sigma 4, since those are the symbols missing from that column, from column 2. Same with the rows. So R3 is missing symbols 1, 4, and 6. So that's why I joined them to those sigma prime vertices. And I'm going to have these star vertices. I'm going to join those with f of j edges to each sigma j. So remember, I wanted symbol 2 to appear twice on the diagonal. So I'm joining those, sigma 2 and C star with 2 edges. And I wanted 6 to appear once. So I'm joining it with C star 1 edges, and same over here with the R vertices. Okay, so basically what they did in the past, maybe this is kind of a common proof technique used for other things as well. Some of you may have kind of seen this idea before, is they find this set of edges that are going to help me place these symbols into these rows and columns. So I'm going to use this graph on the left to fill in this n+1 row. So I want each of my column vertices to have exactly 1 edge, each of my sigma vertices to have at most 1 edge from the set, this green set here. And I want each of these sigma vertices, the sum on each side, to be however many edges, however many times that symbol needs to appear in this new extension to meet those risers conditions. And I want there to be an edge in the set, so a green edge from C star to sigma 2, so the same number here, the same symbol here. So since there's one from C star to sigma 2, I want there to be one from R star to sigma prime of 2. And that's going to allow me to fill in this cell, or this n+1 by n+1 incomplete Latin square, so that all the symbols satisfy risers condition. So we can look, again, column 1, I'm going to put symbol 6. Column 2, I'm going to put symbol 4, and I can fill in that n+1 column as well using this graph on the right here. So you might be asking, how did I find that special set that just lets us do this? In the past, in this example, they kind of added some edges and used like proper edge colorings. But for right now, I'm just going to kind of hand wave it and say you can find it in those big cases. And I can continue to do this, delete these edges, and fill in the next ones. And so in this case, this one is completable. Okay, but I said earlier, if t is less than 2n, which it is in this case, right? Our n is 5 and our t is 8. That sometimes there's ones where you can't kind of use this method. They're not completable. So I like to just throw up an example here. I'm not going to go into too much depth on why. But this purple component is kind of the problem. We can't kind of find that green set that we were looking for because of these kind of purple components. But all of these kind of bad components that we come across have that same property that one of the symbols is prescribed to appear exactly once. So in this case, our symbol 6 is prescribed to appear exactly once. So that means it's a candidate from one of these bad components. And in this case, in this new example here, they do contain these bad components. Okay, so again, that's what led to this kind of conjecture that we proved. So here's our main theorem here. So again, I am assigning the whole diagonal. That's what this sum means. And this time I'm assuming that none of my symbols appear exactly once. And I get this kind of nice clean statement that the resulting Latin square is completable if and only if each of these symbols satisfy that kind of same risers condition here. And I'm gonna go through a little sketch of the proof and kind of hand wave a lot. But these first two cases, I think probably most of us here could do them. If we sat down for a day, you could come up with these yourself. So let's kind of quickly sketch through those. So the first one, I'm going to assume that there's some symbol. So what I'm going to do is I'm going to prove that we can assume this, that all the symbols, we can assume that all the symbols are prescribed to appear 0 times or 2 times. So let me assume that one of the symbols is prescribed to appear greater than or equal to 3 times. And I'm going to define f prime of that value alpha to be 1 less than f actually is. And I'm going to define f prime of j to be equal to f for all the rest of those values of j. And I can use that kind of theorem where this whole diagonal isn't prescribed to complete this Latin square. And I can permute the rows and columns and put alpha in that spot there. And now I have an n plus 1 by n plus 1 Latin square, incomplete Latin square. And I did the kind of algebra down here, but all the other symbols except for alpha satisfy risers condition by the sufficiency of that theorem. And alpha just happens to also work out, the algebra works out, it also satisfies risers condition. So technically we could kind of use this strategy to say all the f values are 0 and 1. But remember, we're kind of avoiding those f values of 1. So I'm going to use this strategy for all f values bigger than 2, so that I can say that the f of j of every value is in this set 0 and 2. So again, quick first step. The second step, t minus n equals 2. This one, again, is pretty quick. So because each of the values are either 2 or 0, we know that we want that same symbol in that diagonal there. And by assumption, we know that alpha already satisfies risers condition. And if we work out that algebra, that means that alpha actually occurs n times in L. So really, alpha already occurs n times in L. I can use just normal risers theorem, ignoring that prescribed diagonal condition, and know that when I complete this, alpha has to occur in this bottom 2 by 2 cell. So if it occurs off the diagonal, I can permute the columns, or it already occurs on the diagonal like we want. So when 2 minus n equals 2, we get this quick case here, where we can complete this Latin square. All right, and then the last two, I'm going to quickly hand wave. But the t minus n is in 4 and 6. That's where we're kind of using that graph approach that they used previously. So it gets a little bit harder because I'm going to try to extend L by 2 rows and 2 columns. So kind of finding that set we need definitely gets harder. But we kind of use a similar approach, figuring out those details to get exactly what we need in that bottom 2 by 2 corner. And then for t minus n greater than or equal to 8, we have a neat little proof too here. So this is kind of new, different than what's been used in the past on these types of problems. So it's kind of similar to that first case. I can take some symbol s and let f prime of s equal 1. And remember, all the other symbols that appear here appear twice. And I can use that same theorem that says if it's not completely prescribed, I can fill it in. And then I can define these AIs and BIs as follows in this picture. So the sets of the blocks of rows and columns shown in the picture. And the Ds here. And so each of these Ls, As, Ds, and Bs form some possible extension of L into an n plus 2 by n plus 2 incomplete Latin square. So they all form this kind of possible incomplete Latin square here. And actually we can kind of get this kind of contradicting ideas here. So for one of these symbols, I can say that S satisfies Reiser's condition. So how do I do that? So if I assume none of them do, that's saying that there's not very many S's in all these kind of these rows and columns here. But we know this is a Latin square, so there's at least n of them up here and n of them up here. And again, a little hand wavy, but we kind of get this contradiction where if it's a Latin square, there's lots of S's. If it's doesn't satisfy Reiser's condition, there's not very many S's, and we get that contradiction. And so again, very, very hand wavy, but a general idea of how that went. So that's kind of the sketch of the main theorem there. And it looks like I'm a little short on time, so I have a little bit of summary here, but I'll go ahead and stop there. Thanks.
Thank you, Stacie. Please. Thanks, sir. Are there any questions?
May I ask a question?
Yes.
What is the difficulty when t is exactly 2n?
Okay, so actually, so in this prescribed diagonal problem, they, in the original proof, they proved that there was examples that were not completable when t was less than 2n. But actually, we've shown now, since we've been looking at again, that there's also examples when t is equal to 2n where it's not completable. This is kind of different, I guess, than the idempotent case, because the idempotent case, the 2n is kind of with those bigger values up here. But for the prescribed diagonal, they kind of get grouped in with this lower case down here. Maybe if for the future directions, we're kind of thinking maybe you could go a little bit further and say more about that 2n since it's kind of on the border of that case. Did that answer your question? I feel like I danced around it a little.
Yeah, rough. I don't think I have enough of a grasp on this to like get a more in-depth answer than that. But yeah, I get the idea. Thank you.
Yes.
Any other questions? I'm just curious about, is that the only way? I mean, this is the unique function to be described, to have this, completing a Latinist square, because if there are some other, maybe we can change the condition to be weaker. I don't know.
Are you saying
so it's a unique way to completing your Latinist square, right?
Yeah,
unique function.
There's not a definitely there's more than one way to complete some of these.
Did you find one? I'm talking about. Is this the only way you complete a Latinist square, right?
So when we kind of find those, like the sets of green edges kind of that I said, there's definitely more than one option at each step. So like I said, they kind of used these, like a lot in the past, they had used proper colorings, and you could really pick any color class of that proper coloring, right, to do each of those steps, and even different proper colorings, right? So you could probably color the graph in different ways. Yeah. That's
nice.
a good question. Yeah, interesting.
Thank you. Thank you for your great talk.
Thanks.